Hello, my name's Mark Diederichs. I'm a professor at Queen's University, where I've taught rock mechanics and rock engineering and done research in those subjects for the last 20 years. I also consult in international tunneling and mining in those areas. I'd like to take you through a journey of my experience with rock mechanics, rock engineering modeling, and use that journey to examine the questions we used to ask those early models, the questions we asked them through the last 20 years or so, and what questions we should be asking today and into the future. My first experience with computing was my own personal Commodore PET, which I had during undergrad university. That's on the left. It still sits proudly in my office. When I started grad school, we had an IBM XT with 640 kilobytes of RAM, two 360K floppy disks, and a Hercules graphics card. We also evolved in our rock engineering group at the University of Toronto to have some other machines, including the Spark station you see on the right. My first experience with rock engineering software was the coding of a boundary element program in the back of Hook and Brown 1980. In the back of that book, there is basic code that can be programmed up even on my Commodore PET with a little bit of input on geometry and stresses and material properties. You can generate a grid from which you can contour the stresses around any opening. Very exciting times. Before that, we had analytical tools to ask how in an elastic material in situ stress can get perturbed by the creation of a circular tunnel. Now with these simple boundary element model tools, we could ask what's the impact of stress magnitude. We could look at orientation, principal stress ratio. Didn't have to be isotropic anymore. We could play around with non-circular openings, multiple openings, try to figure out what the true stress state was elastically inside a pillar. Where around our excavation was the yield strength exceeded? These were big questions at the time. Now, prior to 1988 at the University of Toronto, there are many advanced modeling developments in boundary elements, displacement discontinuity models, discrete elements, finite element formulations. I remember some lattice models, fracture flow models. The primary users of these advanced modeling tools were essentially the creators of the models or their colleagues and sponsors. Also in the 80s, faculty at the University of Minnesota were working on similarly complex advanced models, and they founded the Itasca Consulting Group. In 1984, UDEC was first released for mainframe use. My first experience was with a 3.5-inch disk of MUDEC released for the PC. FLAC was released in 1986 as well for PC use, and you can see some of the early output there. And 3DEC came along at the end of the 80s. At the University of Toronto, John Curran and Everett Hook in 1988 founded the Rock Engineering Group, and they embarked on a mission to make geotechnical analysis software available to practicing mining, construction, and consulting engineers. On the right, you'll see the early version of Phases, forerunner to RS2, and this screenshot right there was one of the most exciting times of my graduate school at University of Toronto when Brent Corkum brought home source code to do automatic meshing around an excavation. My own personal contribution was in the form of DIPS for analyzing structural data. This came out in 1988 in some of the beta versions, originally called StudPlot, and worked its way through a number of versions to what we see today. With this software, you could ask how to interactively determine the importance of structural clusters. You could play with the data and assess and sort the data and filter the data to figure out how you could divide your project into structural domains. DIPS is still in use today. Rocscience now has added kinematic instability tools, which are very powerful. Even in the early days, DIPS fed into Unwedge, which was a structural wedge tool, and you can see one of the original versions here. And this allowed the user to visualize, again, the formulas that were in the back of Hook and Brown 1980 to assess how a three-sided wedge would interact with an opening. And here you can see the original user-friendly sort of CAD-style input and output, which was quite groundbreaking at the time. And this program is still in use today. It's one of the first tools that many tunnelers and cavern designers reach for preliminary analysis and even in some cases support analysis. Using the same formulas from the back of Hook and Brown, end of the 90s, I also developed a piece of software called AWedge, which was built into AutoCAD to do a similar set of analyses, but for discrete wedges in discrete locations based on actual mapping. Unwedge itself lives on. This is just some work I did some years ago in the Brockville Tunnel, which is now open for tourists. It's a fabulous location when COVID's over to go visit. But as part of this feasibility safety stage to reopen this tunnel, we did some LiDAR scans. Those LiDAR scans were automatically turned into stereo nets, and then using dips and unwedge, we were able to show where bolts were needed, but more importantly, where the unstable blocks had already fallen out during construction, and we could retain as much as possible of the original tunnel profiles, just using a simple tool like unwedge. Now, Examine 2D grew from this source code in the back of Hook and Brown, and it was, again, a very simple actual algorithm, but incorporated into a user-friendly framework. And this was, I believe, our first release from the rock engineering group at U of T. And this program today is still extremely useful for education. There's nothing like real-time examination of stress flow around openings. And it's been coded up as well into Windows. And I think there's still a future in Examine 2D. Now, of course, this basic idea can be expanded into 3D, and these models were around prior to the 90s, but their incorporation into 3D user-friendly software and in the form of Examine 3D or Map 3D really revolutionized mining analysis in particular, and complex cavern geometries where tunnels are intersecting. Here we could look at how the interaction of excavations changed the stress field. Could we optimize geometries for the stress? How would large mine openings affect smaller distant tunnels? These were all questions that were now open to be answered through 3D elastic modeling. Now, we knew that the modeling was elastic and that yield was not happening, but as long as we limited our questions within those constraints, it was incredibly powerful. So, interestingly enough, the rise of the user-friendly software coincided with a major celebration of rock engineering in the form of the 5-volume comprehensive rock engineering set published in the early 90s. And one could say that those volumes were a celebration of elite rock engineering done by experts. And this revolution in user-friendly interface development gave way to frontline rock engineering. And I'll say for better, for worse. Of course, lots of people worried that these models in the hands of a non-expert were dangerous. But I would argue that with proper training, the ability to do what-if scenarios, to answer simple questions in situ without going to a consultant, was one of the biggest contributions of the rock engineering group and ultimately Rocscience and of course Itasca as well, following suit. Here you can see some early flak analysis, some early flak results in the elastic continuum. This also became user-friendly in the 90s, and it posed a problem that now we had to figure out what our continuum rock mass strength and stiffness was. And Dr. Everett Hook, of course, was the primary author of the GSI system, which allowed us to characterize the rock in situ and convert that characterization into a factoring for rock mass strength and stiffness. Because we realized that intact properties did not reflect the rock mass properties in the field, and joint property data didn't really have any place in our continuum models. And so at the time, GSI was the only way to get rock mass properties into a model. Now, inelastic continuum modeling we could do in the past without these tools, but we could only answer simple questions about yield in a circular and isotropic stress field. Within a program setting, we could look at yield in anisotropic stresses, yield around non-circular openings. We could experiment with the effective post-yield response and multiple openings. Now, sequencing became a major concern because once rock begins to yield, the path matters. So we could optimize excavation sequence for sequential excavation. And we had the power to examine support and look at stress redistribution for the first time as well. Now, there are many, many forms of continuum geotechnical models today. The Rocscience and the Itasca codes, of course, are just two of the suite of programs that are out there. But the very powerful user interface connected with very powerful algorithms today, I would say, dates back to those early days in the late 80s and the early 90s. Now, I'll pause here just to ask, though, and I'm speaking from the practitioner, from the field engineering viewpoint. when we use these programs for design, are we asking any more sophisticated questions than we did, let's say, in 1980 or in the 1990s? Primarily, we're modeling to find out the depth of yield. We're modeling to find out how much closure there is, or average closure in the walls and roof. What's the load on a liner, let's say, and what are the bolt deformations? So while we have more complicated models and we can view more complicated scenarios, the questions are pretty much the same that we asked back in the 1980s of our analytical solutions. Now, there are some new questions that we can start to answer, and we do. What is the post-yield behavior of a rock mass? That's a big question. Does the post-yield lab response, which we can now measure in our lab experiments, mean anything in the field? How do you model post-yield for an in-situ rock? We have tools, we don't know if they're correct. How about for a rock mass? How do you measure or specify dilation parameters? The volume change after yield in a rock mass. How much yield is too much? If you have a complicated system, material yield does not immediately mean that the system is failing. Now we can also investigate liner moments and shear in our tunnel linings, and not just thrust loads. And we can analyze in a much more sophisticated way the rock support interaction. I'll just tackle a few of these issues. So rock mass strength, post-yield or residual rock mass strength. I would argue that we still have no solid tools to estimate residual rock mass strength. In the paper, I propose a possible solution to this problem. Couple that with the dilation model. We have some guidance from intact experiments. We have some guidance from basically experience. But these are all very approximate tools. And I'd argue that we need more sophisticated versions of these to move forward. One question that's of great interest, both in mining but also in civil construction, is when do pillars or a pillar fail as a system? And we can track rock yield, but that doesn't necessarily mean pillar failure. So mining design works with yielding pillars all the time. For a civil construction project, first we have to define what we mean by failure, and then how we measure that in our models. Now in mining, we use sophisticated 3D mine-wide models along with seismicity to track the yield of the rock mass and the effect that that has on the surrounding rock and other regions. And one of the big questions, of course, is when do two or more of these regions interact, creating sort of a short-term rise in activity at the mine and possibly a dynamic risk. Now, another challenge for rock engineering modeling: can conventional shear-based constitutive models that we've traditionally used in continuum modeling replicate brittle damage and rock spalling, and how do we do that? So in theory, no. Where we have squeezing tunnels, such as on the left, the criterion we use, the model we're basing the analysis on, assumes that everything is shear-based. Whereas we know that brittle fracturing, particularly in the early stages, is the result of extension fractures. So can we still use our continuum models to do design analysis for this types of behavior? The answer is yes. There's been two developments over the last 25 years. One is cohesion weakening friction strengthening, which works really well in FLAC, which is a time-stepping algorithm, and works on the notion that cohesion and friction are not mobilized at the same time in brittle materials. So as you have cohesion loss, you have friction increase, which creates a brittle fracturing mechanism, particularly at lower confining stresses. And on the left, you see the equivalent version of that, which is written for a program like RS2, which has instantaneous drop from peak to residual. You can still do a similar type of analysis to very accurately replicate brittle fracture in a continuum model. And this is very important because when we're trying to simulate situations like this in an access tunnel, the brittle model is the key to giving us the appropriate overbreak estimations and the risk of floor heave. If you combine those brittle criterion with optimized dilation models, we can do much better in estimating support requirements and support demand for brittle rock around excavations such as power caverns here, which in turn leads to optimized support element design and component design. Discontinuum modeling has been around actually longer than some of the continuum tools we have. We do have to ask, does plastic continuum analysis with homogenized rock mass parameters, GSI, accurately represent the real yield mechanisms in moderately jointed rock masses? And if that's not the case, what are the implications for stability, deformation, and design? And are we correctly modeling the mechanics of reinforcement if we smear all of the rock mass structure into an equivalent continuum? I take us back to 1971 when Peter Cundall wrote his PhD, research into rock slope failure. And in one part of that document, he examines a continuum analysis of a slope failing problem and asks, so large parts of the slope exceeded the failure criterion, even though the geometry chosen was demonstrably stable. He concludes that very small movements must occur on the joints in the real situation, completely altering and redistributing the original stress distribution, creating an overall stability. And the question he asks at that time in 1971 was, can failure mechanisms be built into computer programs? And in the appendices of a PhD written about slope stability, you will find the original source code for the ball program and the block program, which we now know of as PFC and UDEC. Now, the key to these early discontinuum models and their analysis was to keep the questions as simple as possible, because these models were incredibly complex, incredibly chaotic. I remember using these in the early days and being astounded by how one small change would change the outcome of the model. So the key here is to ask very simple questions. And this particular analysis from Barton et al. 97 of a hockey cavern in Norway, with the largest cavern, I believe, still to be constructed for civil purposes. The key to that design and the key to the successful application of this new tool were the questions. And the questions were simply, can rough joints modeled with confinement-dependent strength and post-yield dilation create a stable and clamped arch? And how big could that arch be? Was there an optimum sequential construction sequence to achieve that arching? So in other words, letting the rock mass do its own work. And then, can reinforcement knit any mobile blocks together at this large scale to limit localized slip and create a reliable, stable arch? Of course, now we have very sophisticated versions of these discontinuum tools. The answer, however, is very dependent on the specific realization, sort of the random generation of the joint elements themselves. But in actual fact, so is reality. So in a sense, this is the complexity of the model mirroring reality. The challenge is, how do we incorporate or interpret multiple realizations and then use those for a reasonably repetitive and robust design? Now, a lot of questions, small and large, raise their head when we do discontinuum modeling. So do we have the right models for the joint surfaces? There are very many commercial constitutive models for joints out there. Do we have the right one to best represent what's going on our particular fresh, rough, altered, slick-and-sided joint surface? How do we take 50 millimeter lab samples and in direct shear and upscale them to 2D and 3D? Now with these discontinuum tools, we realize that joint stiffness actually has a meaning and beyond just settlement. And how do we incorporate that into the model? What numbers should we use? And is the test actually giving us the right numbers for modeling? How do we measure this behavior and compare it to reality? There's other issues about how do we initialize the joints in their stress field? And what structure do we need to actually model to get the right answer? And what can we just leave as part of the remaining rock mass? In my own work, I've used discontinuum tools to examine how brittle rock fracture processes and pre-existing discontinuities, be bedding or joints, interact to create very large-scale and anomalous failure modes. In this case, brittle fracture interacting with unfavorable bedding planes, in this case volcanic bedding, to create a very localized but very aggressive floor heave. Now we have very sophisticated hybrid tools, if you will. And I've got a couple examples here of FEMDEM from Geomechanica and U of T, and UDEC from Itasca, looking at how rock fractures move up into the rock mass and interact. And these fractures can then also be used in a coupled model to see how permeability of the rock mass increases, etc. Some other issues that we're starting to realize are becoming a very big challenge in complex rock mass modeling. Time-dependent behavior, which we've played around with for many decades. Creep, consolidation, relaxation, degradation, swelling. Whatever the mechanism is, we have numerical models that claim to simulate that behavior, but the models are very simple. They're often phenomenological. They're not very mechanistic in nature, which gives us difficulties when we take lab experiments and we try to upscale them to some realistic properties and then apply them in the complex geometry and geology of our models. We have no tools for estimating time dependency of real rock masses. And there's certainly no guidance for joint behavior in a time-dependent sense. So big challenges as we move forward, particularly in areas like nuclear waste management. And then we have the challenge of hydraulic coupling. In low porosity jointed rock or high porosity rock, we have tools that allow us to look at drainage, effective stress. The image on the right is from Beck Engineering, a full line-wide, fully hydraulically coupled jointed rock mass model, looking at how rock mass movements around the mine affect the structure, which in turn affects permeability, which in turn affects the hydrological regime. But how do we understand the fluid flow and the fractures in the rock mass at depth in a constitutive way? How do the stresses affect the permeabilities? We have models for that, but how do we validate it, verify it? So I want to go back to a paper that was written in 1988. It was part of the required reading when I was a grad student at U of T, Starfield and Kundal, Towards a Methodology for Rock Mechanics Modeling. And they make the comment that there was a time when the focus of attention in rock mechanics was on laboratory and field measurement. Models which existed in a mainframe capacity were generally thought to be irrelevant or inadequate. This was probably due to the lack of geological detail, and this lack of geological detail was a major stumbling block to early acceptance of modeling in rock mechanics. That's a quote from the paper. I would say that here the failure was in the expectation that the models should themselves tell the whole story. I see this in students who create their first model, or people who are new to modeling. They expect the program to create both the questions and the answers. Whereas models are designed to be asked very specific and constrained questions, and then the answers should be dealt with within that context. Now, that said, greater complexity is terrific. The ability to include more detail is welcome, but only up to a point. So the downside of more complex, apparently more realistic models is that the modeler, and again, this is a quote from Starfield and Kundal, the modeler becomes hooked on an addictive credo that more detail implies a better model. Bigger and better models in turn need more data, leading to the need for more field and laboratory measurements. Now the problem is that those measurements are costly and are not always the right measurements. We don't currently do routine site investigation to collect data to feed into these complex models. We build models because the real world is too complex for our understanding. It doesn't help if we build models that are too complex just because we want them to be complex. Another quote from Starfield and Kundal, the art of modeling lies in determining what aspects of the geology are essential for the model. The challenge is to turn that art into a methodology. And when we have these sophisticated, complex, all-singing, all-dancing models, how do we know the results, however impressive, are valid and correct? So there are problems where we have lots of data, there are problems where we have lots of understanding, and there are problems where we have neither or both. And this idea of verification, calibration, validation comes into play here. I would argue that certainly if we don't have any understanding, we don't have any data, we shouldn't be modeling. If we do have some understanding of our problem, modeling can be very powerful to guide us in the questions we should ask, either of our model or of our investigations. We need to check for sensitivities for things we don't know. If we have lots and lots of data and don't really understand our problem, we're faced with empirical modeling, I would say. And this modeling can be calibrated. We can measure closure in a mine or a tunnel, but we really don't know what's behind that closure. So some of the questions you might want to ask of your model are, can you identify the behavior modes and the mechanisms? Do you need a different model or a more complex model to accurately represent that? And then what are the critical modes of failure? And within those, what are the limit states that you're trying to get to? And then in that context, are you getting the right data for the model? These are questions that you need to ask before you start. And one of the things that's a bit of a problem when these models get very complex is how will you measure your answer? I mentioned pillars. How do you know that the pillars are still performing a useful function? Even though they may indicate yield, there may be some deformations. Closure in rock engineering is actually a tool that we use to allow the rock to support itself. But how much is too much? What are your design metrics? What is in the model and what is ignored? In the old days, we knew our models had limitations. We bracketed reality with some bounding cases and we moved on. We didn't assume that our elastic model was telling us everything we needed to know about the rock mass. As we get more complicated, we lose sight of what the limitations of our model are. So we validate first. Validation is the most important thing you can do for your model. Calibration can come later. So a little philosophical piece here to finish up. I would say prior to the 80s, modeling was an elite activity. People with expertise running the models that they'd written. One of the great contributions of the 80s and 90s was that this process was socialized so that people involved in real projects in construction and real mining could actually do the modeling themselves. Now, of course, this had some issues if those individuals didn't have the skills to run those models, but that was tempered by the fact that the modeling was done on site with the rock in question right nearby. Now, modeling has once again become an elite exercise, I would say, with these very, very sophisticated, highly powerful, fabulously complex models. And that's fine. But who's asking the questions now? Who's making the decisions? And for this process to work, I'd argue that what's the interaction between the model experts and the construction and geology experts in the field? So I would argue that this process seems to be done fairly well in larger scale mining operations, where the interaction between the modeling groups and the mining groups seems to be quite institutionalized and quite robust, and the interaction is quite powerful and productive. However, in one-time construction projects like tunneling and cavern construction with geological uncertainties, this approach can only be effective for either initial and especially for observational design if there's a two-way relationship between the modeling and design teams, and that relationship has to continue through construction, and it has to be receptive to new observational inputs. And most importantly, and this might be a dream, this relationship is unhindered by contractual constraints such as fixed design or the fear of claims. Modeling is a tool. It has to be recognized by all that for these complex projects with uncertainties that the conclusions may and probably will change as new data emerges. And we have to be willing to accept that outcome and not hide behind contractual constraints. I love this quote, still relevant today. Dr. Everett Hook told me this while I was hunched over my computer, mindlessly typing away. Never turn off your brain when you turn on your computer. In this world of modeling consultants and expert modeling, I would say the same applies when you ask somebody else to turn their computer on for you. So if you're on the front lines, stay engaged in the modeling process, even if someone else is doing the modeling for you. So thank you. I'd like to thank Everett Hook, John Curran, Reginald Hama, Eric Eberhardt, Giovanni Grasselli, my colleagues Jennifer Day, Gene Hutchinson. Had great conversations with David Beck on this paper. Omid Mahabadi, Kathy Kalinchuk, Evan Drussel, Caitlin Fisher, and two individuals who I've just had great conversations with in the past, David Sainsbury and Joe Carvalho. And there's many, many more who have contributed to my thinking on this issue. Thank you, and we'll be open for questions.